An HTTP GET request hits a REST API. The critical element is the sequential account ID in the URL. A user intercepts the request and manipulates the sequence, changing their ID to a victim's. The server accepts this, delivering the victim's sensitive data. The World Wide Web security community, OWASP, classifies this mechanism as Broken Object Level Authorization, or BOLA. They rank it as the single most critical vulnerability affecting APIs today. The failure occurs between identity and permission. The system successfully authenticated that the user was logged in, but executed no checks to verify if that specific user had the authority to view the newly requested data object. Relying on the implicit trust of object identifiers at the endpoint turns a routine API request into a mechanism for a data breach. Modern software development has moved away from single monolithic applications. Systems are now built using distributed microservices, small autonomous components handling specific business functions. In a monolith, components communicate through local internal function calls. In a microservices architecture, those local interactions are replaced by remote, network-based API calls. This architectural shift expands the attack surface. Because each microservice relies on remote network requests, every individual node becomes a potential BOLA target. Failing to secure this inter-process communication exposes organizations to severe legal penalties. Privacy frameworks like the European GDPR and the California Consumer Privacy Act hold companies strictly liable for unauthorized data exposure. Regulators, including the Federal Trade Commission, are expanding enforcement activities and issuing multi-million-dollar fines against organizations that fail to secure their internal data practices. A firewall at the network edge cannot protect hundreds of internal APIs communicating continuously. Security must move down into the routing infrastructure and the object-level logic. We can see why standard defenses fail by looking at the backend environment. This Node.js code shows the routing logic for the vulnerable bank account endpoint we examined earlier. This flowchart maps the first defensive layer in the code. The middleware executes two steps. It validates that the client provided an authentic access token, and it checks the token's general scope. The second defensive layer confirms the user holds a read scope for accounts. The user has a bank account, so the general read account scope returns a pass status, and the request moves forward. Here is the logic gap. The code verifies the user is allowed to read accounts in general. It contains zero logic to check if they own the specific account ID they just typed into the URL. A common industry workaround is to hide the sequential account numbers, replacing them with long, random alphanumeric strings called GUIDs. Obfuscation is not a security measure. If a GUID is leaked in a message or discovered through an exploit, the authorization bypass remains fully exploitable. Fixing BOLA requires abandoning generic token scopes. The authorization mechanism must map the user to the precise object requested. To solve this, we zoom out to the macro system architecture. The National Institute of Standards and Technology provides established guidelines for securing microservices infrastructure. This network topology shows the first layer of defense, the API gateway. It sits at the edge of the enterprise network, managing all north-south traffic, meaning requests entering the system from external clients. The gateway executes critical defensive capabilities, specifically rate limiting and throttling. This prevents attackers from rapidly scraping the API or brute forcing object IDs. Deeper in the stack, we introduce the service mesh. This infrastructure layer secures the east-west traffic, the internal communications moving directly between the microservices themselves. The service mesh separates its architecture into two distinct modules. The control plane configures security policies and gathers telemetry, while the data plane proxies the actual application request traffic between service instances. The mesh enforces mutual authentication and strict service discovery. This ensures that only explicitly authorized microservices can talk to one another over the internal network. It also utilizes a circuit breaker feature. If an attacker compromises a service, the mesh automatically cuts off traffic, preventing a total network collapse. Gateways and meshes lock down pathways to prevent broad failures, but the final, granular data access decision still occurs at the specific API endpoint. As an application scales into hundreds of microservices, maintaining consistent authorization logic becomes a management bottleneck. One solution is to extract that logic into a centralized, specialized model. This graph represents relationship-based access control, or RBAC. It is a framework designed to handle highly complex, interwoven business rules by focusing on how entities connect. Applied to our bank example, a user-specific relationship to an object dictates their exact permissions. One user is the owner, while another might be a branch manager with access to multiple accounts. Implementing this is called fine-grained authorization. First, you define the relationship model. Then, you store the live authorization data representing the state of your system as stateful tuples. In the final step, you replace the vulnerable middleware code with a centralized SDK check. It queries the fine-grained authorization engine, verifying the request against the established relationship tuples. By evaluating every request against live tuples, the system ensures that access is only granted when a specific, authorized relationship is verified. A system vulnerable to BOLA is inherently non-compliant with international data privacy law. The inability to map exact object-level data relationships is a direct violation of the core requirements of the European GDPR, which mandates that every processing activity have a documented, lawful basis. These same technical failures violate consumer rights and opt-out mechanisms mandated by California's CCPA and CPRA. You cannot honor a consumer's request to delete their specific data if your internal architecture cannot isolate exactly who has access to it. Under privacy law, the entity determining the purposes and means of processing personal data is classified as the data controller. The controller bears the primary legal liability for implementing technical safeguards. Regulators also require a formal data protection impact assessment whenever large-scale processing of sensitive data introduces a high risk to consumers. This demands clear proof of architectural security. Abstract legal terms in data privacy regulations directly dictate the need for precise, low-level technical architectures like service meshes and fine-grained authorization. Privacy by design is the legal doctrine requiring organizations to embed data protection into system architectures from their inception, rather than adding it after development. Integrating a service mesh and fine-grained authorization securely incorporates these principles into the technical framework from the outset. Defeating BOLA attacks requires moving away from generic token scopes toward the precise verification of relationships between users and objects. In a modern distributed architecture, engineering a rigorous security infrastructure and achieving regulatory compliance are the exact same task.